So I have just a little bit of bad news for you. We did this graph. We looked at all of this stuff here. The only problem is that helps you to understand the law of conservation of energy, but none of your problems you will have are going to look this way. They're actually going to look something like this. We have a book that's thrown upward at 25 meters maximum height that it's going to reach. That's what the problems are going to look like, right? So we have this book that gets thrown upward. Just like our previous problem, it leaves the ground at a speed of 25 meters per second, right? And we want to know the maximum height. We want to know the height up here that it's going to reach. So the way that we're going to do this is really, really similar to the work energy theorem problems that we did. And that is to draw a very, very simple picture, which just is a simple arrow like this. And then I'm going to label that arrow with EI at the beginning and EF at the end. We still need to decide what kind of energy these things have at the beginning and at the end. When we did work energy theorem, we had three possibilities. The first possibility for energy type was potential. Remember, you know you have potential energy if an object has height. The second type of energy possibility was kinetic energy. We know that an object has kinetic energy if it has speed. Number three for us with work energy theorem was zero, but don't write that down because we're not going to have zero on this one. Remember, the law of conservation of energy says that energy is the same everywhere in this entire trip, which means however much EI is, EF is the same. So if we have zero anywhere, that means it's zero everywhere, which means nothing's actually happening and something's wrong. So we're not going to have zero. Our third possibility is actually going to be both potential and kinetic energy. Because if you think about it, everywhere in the middle of this flight, this object has both height and it's also moving. It has speed and height at the same time. So if you have both speed and height at the same time, that means you have both potential and kinetic energy. So those are our three choices for energy types with conservation of energy: potential, kinetic, or both. All right, so let's clear this off a little bit and let's start our problem. Again, EI at the bottom, EF at the top. What kind of energy? Well, I know that we are moving at the bottom. This thing is moving at 25 meters per second. And at the very bottom, the instant I throw it, it has not gained any height yet. The height down here at the bottom is zero. So if there's no height and there's all speed, that means initial energy must be kinetic. EF at the top. We want to know the maximum height that it reaches. You should know, hopefully you already know this, that at this maximum height, it's going to stop for just a minute. So the speed at the top is zero, which means there's no kinetic energy up there. So if there's no kinetic energy, but yet it has height, at the top, it must have all potential energy. So for this one, we're going from kinetic at the bottom to potential at the top. Now let's work the problem. The way that we start all conservation of energy problems is with basically a mathematical statement of what the law of conservation of energy says, which says that the energy stays the same. That means that however much energy we had at the beginning, it has to be the same at the end. So EI equals EF. This right here is how you start all conservation of energy problems. And whatever happens in between those two places, the total amount has to stay the same. Now, the next line right here is so incredibly important, and a lot of people mess this up. This right here is where you have to know what decisions you made for energy types. And if you don't make those decisions, you can't really do this step. EI, we said EI was kinetic energy, and the equation for kinetic energy is mv squared over 2. So that's what I'm going to enter in, substitute in for EI. EF was potential energy. Potential energy is mgh. So that's what we're going to enter in for EF. mv squared over 2 equals mgh. So the kinetic energy down at the bottom, however much that is, has to equal the amount of potential energy at the top. And we're going to use that statement to solve for h, the height. Now, let's plug in numbers and solve. And you might be thinking, but wait, Mr. Valls, we can't solve this because haven't you noticed that we don't have mass. It's not there. Yes, you're right. But here's the cool thing about conservation of energy problems. It doesn't really matter what the mass is, to make a long story short. If I divide by mass on both sides algebraically, it simply goes away. And it doesn't matter what the mass is. And if you don't believe me, just pick a mass. Just choose 9. Just put 9 in there for the mass, plug it in and solve this problem. You're going to get the same thing I do in just a few minutes, but I'm going to do it quicker. Mass goes away. And that's true with all COE problems, all conservation of energy problems. So you might want to write this note to yourself. With all conservation of energy problems that we will do in this class, mass doesn't matter. As long as this system is closed, as long as we don't have any friction, there's no friction happening, we can get rid of the mass, which is really, really great, because that means this equation now actually just becomes v squared over 2 equals GH. So we can plug in numbers and solve. We started with a speed of 25. That has to be squared all over 2. We know that G is 9.8, and we're solving for H. 25 squared is 625. 625 divided by 2 is 312.5. Still got our 9.8 H over here, and our last step will be to divide by this 9.8. And if you do that, you will find that it reaches a maximum height of 31.9 meters. This part right here, we actually did really, really similar to this last part in a previous problem. So this is a really useful way to figure out how high this thing is going to go, simply based on the speed it started with. Because here's the point. When we threw this book up in the air, we gave it some energy, and the amount of energy it has, because it only had kinetic energy, the amount of energy it has is based on its mass and its speed. But because the energy on the other side is also based on mass, that means mass cancels out. So the energy that the object has is simply based on the speed at the bottom, and that amount of energy has to stay the same at the top. So we used that equality to then solve for this height, which was 31.9 meters. Let's look at another problem like this. Another free fall problem about a wedge of cheese. I don't know why it's a wedge of cheese, and this picture here is certainly not a wedge of cheese, and it's certainly not dropped. Let's change this. That's a mistake of mine. This wedge of cheese is being dropped from a height of 22 meters, right? I'm going to do this a little bit faster. Height of 22 meters. How fast? We want to know its speed. How fast will it be going when it impacts the ground? I want to know the speed down here. I want to know V. All right, so here we go. Same thing. EI at the top, EF at the bottom. Go ahead and make your decision now for what kind of energy. Is it potential? Is it kinetic? Or is it both at those two locations? And again, we know those locations because here's the maximum height that it's dropped from and then impacts the ground. That's at the bottom. That's how I know that EI and EF are at the top and the bottom. So what kind of energy? Make that decision while I write EI equals EF, because that's how we always start. Hopefully you decided that EI was potential energy and EF was kinetic energy. Potential at the top, kinetic at the bottom. Memorize that. I'll say it again. So at the top, we're going to say mgh because that's our equation for potential energy. And EF at the bottom is kinetic energy. So kinetic energy is mv squared over 2. Once again, we don't have the mass of this cheese, but once again, it doesn't matter. Mass doesn't matter. We could have a humongous wedge of cheese. We could have a really small one. And as long as there's no air resistance from friction, we know that they're going to hit the ground at the same time, as we saw a long time ago in that video of the bowling ball and the feather. So let's plug in some numbers here. We know that G is 9.8, drops it from a height of 22. Equals V squared over 2. V is what we want to solve for here. All right, so we're going to start by multiplying by 2 to get rid of this 2 in the bottom. Multiply by 2 to get it out of the denominator. And we got 2 times 9.8 times 22. If you plug that in your calculator, you will get 431.2 equals v squared. And the last step, if we're solving for something that is squared in the equation, to get rid of that squared, we got to do the opposite, which is to take the square root, right? So this is the operation we need to do right here, the square root of 431.2. If you take the square root of 431.2, you will find that the speed at the bottom is 20.8 meters per second. All right, so to recap, we decided that the top was potential energy, so we plugged in mgh. We decided that the bottom was kinetic energy, so we plugged in mv squared over 2 for EF, initial and final. We got rid of the masses, plugged in our height, solve it with algebra, and we get 20.8 meters per second.